As we look at the second section of our applications from section 5.5, we're going to be talking today about growth and decay. Our growth and decay factor is going to be really either functioning either on an increasing manner or on a decreasing manner. And depending on whether it increases or decreases, we're going to have things like population growth, we're going to have things like half-life, and so the real question is going to be whether things increase or decrease as we're working through our problems today. This function of increasing and decreasing is going to be purely a function based on the value of k. First, our examples we're going to be looking at are going to be taking a case of do they increase or decrease, and then do they then increase or decrease based on that value of k. All right, let's talk about defining some of our variables here. Our initial n of t value is going to be the population. Really sorry about the pen here. It's going to be the population at time t. Second, our n sub 0, just like everything, whenever we have an n sub 0, we're always going to have, that is going to be the initial population. And that's going to be at the beginning of our cycle, whatever the beginning of our cycle is. Our k value is going to be the rate of growth in our function. It might be the rate of decay in our function. And if k is positive, we're going to have a growth factor. Okay, so I need you to remember k being positive, being a growth factor. And then second, if k is a negative number, then we are going to have decay. And we're going to be looking at some problems with decay on the back. So it all depends on what our k value is for either growth or decay. And then finally, t is time, as it has been in the past. However, you need to realize that the t does not have to be in years. And I need to emphasize that because it could be the number of cycles. Many times one cycle will be 1 year, but in this case our cycle is going to be our variable t. So let's look at our first example. And if you don't have your calculators, you're going to want to get those out because we're going to be functioning and using our calculators here as we function. So let's talk about our important information in this first one. We have 85 frogs as our first thing. Our population growth is 18% per year. And so that is our key part. And then the third is the fact that it does grow exponentially. It's not doubling, but it's growing exponentially. So let's kind of write our function very simply. We're going to have f of t equals our initial amount, which is 85, times e raised to our percentage. Now 18% obviously is 0.18 times t. Be very careful as you write your t's that you do a cursive t so you don't have a problem there. So that's going to be our function model representing this growth. Now, after 6 years, very simply, all we're going to need to do is we're going to need to plug in and find the value at 6 years. Nothing new here, so 85 times e to the 0.18, but times 6. So as we work that out, I'm going to flip over to Desmos calculator, and here you can see, hopefully, as we have a Desmos calculator over here on the left, we have 0.85 e raised to the 18 times 6 is 250.2977. So that's going to be our value here. You could do this on your calculator just as well, but the point being, at 6 years, we're going to have about 250 frogs, because obviously we're not going to have a partial frog as our possibilities. Once again, that was desmos.com, and very simple to do that. All right, now our next idea that we're going to be looking at is finding the value and the number of years required for the frog population to reach 600. So this is a very straightforward problem. All we're going to be doing is we're going to take our standard function, which is 85 e to the 0.18 times t, and the question is, when will it equal 600? Now, to do this, we're going to divide both sides by 85. So we get 600 divided by 85. We'll deal with that in a little bit. I have an exponential here, and so to get rid of an e to a power when the variable is in the exponent, we're going to take the natural log of both sides. So we have the natural log of 600 over 85. I'm going to keep to my exact numbers at this point. And so 0.18t is equal to the natural log of 600 divided by 85. Okay? Now, going from there, that means t is equal to the natural log of 600 divided by 85, all divided by 0.18. You can put this into your calculator, and very simply you can see this is 10.857 years. Now, we do have a possibility we can also, if we need to, use a calculator to graph. And you could use your calculator and you can zoom in. I'm going to choose to use Desmos here and just kind of show you what I did. Here you see at the top I have my red line, which is my function, and I've put that in for 85e to the 0.18t. And the problem is, you see my normal exponential function up here at 15, it's kind of going out of sight. And so I could scroll up as far as I needed to try to see this, but instead what I'm going to do is I'm going to zoom out. And we're going to try to zoom out until we get to 600. Very quickly, we're going to get about to 600, and now I'm going to come into my middle section and I'm going to zoom in where my value is 600 to see how accurate I can be very, very quickly using Desmos. So here we are at 600, and if we click right on that one spot, we're going to get our value for 600, and see here you can see at 599. We're just going to arrow up a little bit. 10.857. So it's the same value using Desmos and a graphing function as it is had we used our TI calculators, just to show you what the normal function is. And you can see from here what an exponential truly looks like. It is very, very much like a right angle, except at the extreme vertex where that point will be, a little bit of a curve. All right, well, let's move back to our problems. And let's kind of take a look at our next page. Here, we're going to be talking about half-life. In half-life, our variable of k, if you remember from the first page, is going to be a negative. However, we're not told what the variable of k is. So we're going to take a look at our basic function. Our basic function, once again, is f of t equals 10 times e to the k times t. Now here, we don't know our value of k or t, but they do give us a scenario where we have the first part, the half-life is 30 years, and we have a 10-gram sample. So to work this out, what we're going to do is we're going to say, hey, after 30 years, which is one cycle, okay, we're going to say, what's the value that we're going to have? Well, that value that we're going to have after 30 years, I hope you realize, is 5, because it cuts the value in half after one cycle. So here's our input, there's our output, that's our x, that's our y, and so let's write an equation now that we can put that in. So 5 is equal to 10e raised to the k times our 30 years. Well, let's work this backwards and go from there. So we have half the amount left when we have e to the 30k. Simple to solve. Obviously take the natural log of both sides. Natural log of e raised to the 30k. Now I hope you're getting to the point where you don't need to write the natural log of e to the 30k, but instead you can jump right to this step where you just say 30k equals the natural log of 1/2. Next step, obviously, is you're going to divide both sides by 30, and you're going to get a k value of negative 0.0231. That means our final function, if we're going to write this out, is 10e raised to the negative 0.0231 times t. So the way we did that, once again, is we knew our initial value of 10, one half-life of 30 years, and our new value of 5 giving us our function. Now that we know our function, let's evaluate that for 80 years. And notice we don't have to do a specific multiple of 30 years. We're going to go with 80 years. So our function of 80 years is just going to be 10 times e to the negative 0.0231 times 80 as our exponent. When you plug that into your calculator, you're going to get 1.576 grams left of our cesium, I believe is what we're talking about here. So 80 years, we started with 10 grams. After 80 years, we just have 1.576 grams. Let's take it the reverse way and say, hey, instead of doing a time, let's talk about what if we only have 2 grams left. So our original function, let's write that over again, f of t equals 10e raised to the negative 0.0231 times time. Instead of saying plugging in our value of 80, let's say when are we going to have 2 grams left over? Divide both sides by 10. That gives you 1/5 e raised to the negative 0.0231 t. Take the natural log of both sides. Negative 0.0231 t. And now we're going to divide both sides by negative 0.0231. So, if we plug that in, how long is that going to be? About 69.673 years. So, we've talked about a couple different scenarios for solving different types of problems. Hopefully this is helpful as we're looking at our half-life of population growth and decay.